Hi. The project I'm going to discuss today focuses on inundation of transportation infrastructure in Hampton Roads region in Southeast Virginia due to storm surge, and how will sea level rise impact that flooding. The work is funded by Virginia Department of Transportation, VDOT, and the DOT through Mid-Atlantic Transportation Sustainability Center, MATS UTC. And the work has built up on my former student's Luca Castrucci master's thesis, and he's a co-author in this presentation. Okay. So flooding is an important, is a critical problem in our region. I'm showing on the left a figure of flooding in a historic area in Norfolk, Hague, very close to downtown Norfolk. This area houses important businesses, uh, historic residential buildings, and also houses the Norfolk General Hospital, which has the only level 1 trauma center in the region. Flooding is an issue in this area, as you know, as general problem as it is a general problem in the region, and this flooding issue, nuisance flooding issue, is going to increase in the future, as you can see in the figure on the right. The future projections show that there is an increasing trend in nuisance flooding, and this trend is very well correlated with sea level rise in the region. Okay, so why do we care about flooding of transportation infrastructure? Obviously, our daily activities are disrupted, businesses are disrupted, evacuation in case of extreme events are going to be impacted, and as well as emergency operations. So the question is, how does sea level rise impact extreme inundations? Here we are going to look at two storm scenarios, 10-year and 50-year storms with annual likelihoods of 10 and 2% respectively. And the sea level rise scenarios we're going to investigate are intermediate high, high, and extreme based on NOAA's recent report authored by Sweet et al. So in terms of the scenarios that we select, if I in this figure, I'm looking at both the scenarios for Swells Point, located in Norfolk, Virginia. How does that change from 2020 to 2100? And I'm also showing the historic trend. So based on historic trend up to 2020, we are following intermediate low curve. But for infrastructure planning purposes, it is generally recommended to look into higher estimates. So we selected intermediate high, high, and extreme in this study, and time horizons we selected were 2030 and 2070. Our approach was to develop a hydrodynamic plus wave model at two levels of nesting: a high resolution, a low resolution large grid that encompasses Chesapeake Bay will provide boundary condition, a wave, and water level for a nested high resolution grid that focuses on area of interest. And the resolution can go in this curvilinear grid can go down to 10 meter around the critical spots and up to 90 meter away from those spots. So how do we identify critical spots? In this study, we identify critical spots as bridges. So first focused on bridges because of their critical importance for the overall network. And we identify critical bridges based on the traffic volume and elevation. So any bridge that was below 3.5 meter above present water level was considered, and in terms of elevation and in terms of volume, traffic volume, with traffic volume higher than 30,000 average annual weekday traffic was considered to be our threshold. With these limitations applied, we came to 8 bridges. So how do we came up to 3.5 meter threshold? Well, this is what we defined. And this is essentially under intermediate high scenarios, 2100 water level plus a very common storm, 50% chance, annual chance storm. So if a 2-year storm essentially added to 2100 water level gives us this elevation. But again, you can use different definitions. To examine the vulnerability to flooding in these critical bridges, we defined a flood intensity index, which is essentially a collective, which is essentially the summation of inundation at different scenarios. Again, there are other ways to define this this measure, but the goal was to include most bridges as much as possible into analysis, and averaging for our case didn't really work. So this is the way we defined it. But the evolution with time, with sea level rise condition is what we are looking for. And also what we were interested in was to see how this approach compares to the linear widely used bathtub approach, widely used by stakeholders still. So how do we compare the two? For low scenarios with 2030 as time horizon and 10-year storm, bathtub model and the hydrodynamic model give very close estimates. But as we increase the intensity of flooding and time horizon, the estimates start to diverge. So for 2030 with 50-year storm, bathtub model actually underestimates, whereas for the more intense scenarios, bathtub model consistently overestimates flooding. So overall, we can say that the bathtub model is giving us conservative estimates, which is consistent with some of the previous studies as well. So this index was looking at the critical spots, but to get an idea of the overall vulnerability, we have to look into a more continuous measure. Flood volume or flood area can serve that purpose. So flood volume in city of Norfolk, which we selected as our model had the most coverage, consistently again increases with sea level rise, and linear estimate of bathtub model consistently overestimates flooding. So once we take into account all the points in the model, then we get a better view of the nonlinearity in the storm surge and sea level rise combination. And obviously there is nonlinearity involved. Okay. So we also looked into the percentage of flooded roadways as another measure of transportation vulnerability. Essentially, what is the length of, so we did GIS analysis, we found out what is the length of flooded roadways under each scenario, and divided that by the total length of roadways in city of Norfolk. And flooded roadways and the flood area, as you can see, closely follow, but then they are not exactly the same. So some GIS analysis needs to be conducted to get a better view of transportation vulnerability in this regard. So successes of the project, we developed a hydrodynamic wave model that we can expand to other applications such as sediment transport analysis, which is also another important aspect. Coastal erosion is a critical problem in this region. There are nonlinearities involved in combination of sea level rise and a storm surge. We were able to quantify some of the vulnerabilities in transportation infrastructure, and we also were able to highlight some limitations of our modeling approach, which I will discuss in the next slide under challenges. And we also established partnerships with local stakeholders, Norfolk and VDOT specifically. What are the challenges? So we are looking into flooding of an inland infrastructure without taking into account enough of inland processes. So storm surge and rainfall often coincide, but in our model, we did not look into that. So compound flood modeling is essential to get that improved. And in fact, I'm showing here a figure that compares storm surge model output with the compound modeling work that we recently did, and overland gauge. And as you can see, with the storm surge model, we have about 15%, 50 centimeter overestimation of what is observed. This red line shows that. And this is an overland gauge, by the way, not a tide gauge. As we add as we couple the model with the inland model, we immediately see improvement, and the error is down to 3 centimeters perhaps. So it is important to take into account inland processes, precipitation-driven flooding, drainage systems, other stormwater infrastructure measures. So, but even if we do that, we are missing some of the dynamics. Our modeling, specifically storm surge modeling, uses bare earth digital elevation models, and the dynamics of interaction between flow, structures that will impact flooding, that will impact forces on the structures is missing. So we have to move beyond that to get a better estimate of vulnerability of our infrastructure. In terms of transportation infrastructure, another challenge is how will we define it? We look into flood vulnerability, but then the flood vulnerability in terms of physical flood depth that we observe, we estimate, we project to happen. But how will the network be impacted by that? The connectivity between the roads, the access to certain areas, how will that be impacted? That also will have to be counted in the transportation vulnerability. And finally, how we have to find a way to transfer this technology to stakeholders in a way that is usable by them. With that, I thank you, and I put up 2 references that I used. We have a publication coming up in Natural Hazards Review on the storm surge model, and another one in review on the compound flood model. And with that, I will be happy to take any question, and I'll end my presentation.